All right, hello everybody, and welcome to the second lesson of Unit 3, which is on properties of solids. Today we're going to look at the intermolecular forces and how they can explain the physical properties of a material. We're going to learn how to explain the connection between particulate level and macroscopic properties of a substance, and we're going to do that using models and different representations. And you're also going to be able to explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and the interactions between those particles. Before we move on to 3.2, I did want to go over two practice questions to solidify your knowledge from 3.1. The first question says, the table above shows the structural formulas and molar masses for 3 different compounds. Which of the following is a list of the compounds in order of increasing boiling point? So if we want increasing boiling point, we are looking for increasing strength. So we need to look at these 3 covalent molecules and figure out which one has the strongest intermolecular forces and which one has the weakest intermolecular forces. So remember, when we're talking about the van der Waals forces, our weakest usually are London dispersion forces. Then we have dipole-dipole forces. And finally, we have hydrogen bonding. So typically, hydrogen bonding is stronger than dipole-dipole bonding, and typically, dipole-dipole forces are stronger than London dispersion forces. So looking at these 3 molecules, we can see they all have similar molar masses. And when you have similar molar masses, more than likely you're going to have similar London dispersion forces. So we're not going to have any exceptions to this trend that I just drew there. So we're just going to go ahead and look at these 3 molecules and see what types of intermolecular forces they have. So first, looking at acetone. Acetone has this double bonded oxygen here. We know oxygen is very electronegative, which means this is going to create a dipole on this molecule, and that is why this molecule is a polar molecule. Now, because there is no hydrogen attached to that oxygen, it cannot partake in hydrogen bonding. So this would just be dipole-dipole forces and London dispersion forces. Remember, all covalent molecules are going to have London dispersion forces. Then moving on to butane, all we have is carbon-to-carbon bonds, which are nonpolar, and carbon-to-hydrogen bonds, which are also nonpolar. So this is a nonpolar molecule. And nonpolar molecules only have London dispersion forces. And then moving on to 1-propanol, we have our carbon-to-carbon nonpolar bonds and our carbon-to-hydrogen nonpolar bonds, but we also have this hydroxyl group, which is very electronegative on this oxygen, and it does create a dipole or a polar molecule. But on top of that, it has a hydrogen that is connected to an FO or N, and because of it, this molecule can partake in hydrogen bonding. So this molecule has hydrogen bonding, it has dipole-dipole forces, and London dispersion forces. So if we're looking for increasing boiling point or increasing strength, we're going to start with the weakest. The weakest, since they all have similar London dispersion forces, would be butane, because it only has LDFs. Then we will have our acetone, which has a dipole-dipole forces, but does not have hydrogen bonding. So acetone will be in the middle. And then we will have our strongest intermolecular forces, which will be hydrogen bonding, with our 1-propanol. So the answer for this one would be B. Our next question says a mixture containing equal numbers of moles of ethyl acetate and butyl acetate was separated using distillation. Based on the diagram shown above, which of the following identifies a substance that would be initially present in higher concentration in the distillate, and correctly explain why that occurs? So quickly going over distillation, we have a solution in this flask here that contains 2 liquids. It contains ethyl acetate and butyl acetate. What happens is we heat up this liquid, this solution, and the substance with the lower boiling point is going to start evaporating up this tube and condensing down this column until it reaches the distillate container there. So if we want to know what is initially present in higher concentration in the distillate, that's going to be the substance that has the lower boiling point, because that will evaporate from the solution first. So looking at these two liquids, we have ethyl acetate and butyl acetate. They have the same functional group here, but what's different is our number of carbons. So butyl acetate has more carbons, which means it has a much bigger mass than ethyl acetate. So both of these are polar molecules, which means they both have dipole-dipole forces, and they also both have LDFs. However, because butyl acetate is so much bigger than ethyl acetate, its London dispersion forces are going to be stronger. So butyl acetate will have a higher boiling point, and ethyl acetate will have a lower boiling point, which means we know that ethyl acetate will be a higher concentration in the distillate when it first starts distilling. So we know ethyl acetate is going to be of higher concentration, so it's going to be either A or B. Then we need to look at our reasoning. The first one says because it has fewer carbon-to-carbon bonds to break. While that is a true statement, it's not necessarily the reason why it has a lower boiling point. And B says because it has a shorter carbon chain and weaker London dispersion forces. And this is the important part here. So yes, it does have a shorter carbon chain, which is also fewer C to C bonds. However, this one says it has weaker London dispersion forces. So B would be a better answer than A. All right, so moving on to 3.2. Many properties of liquids and solids are determined by the strength and types of intermolecular forces that are present. Vapor pressure and boiling point are directly related to the strength of intermolecular interactions. This is because intermolecular interactions are broken when a substance vaporizes. So something with weaker intermolecular forces is much easier to vaporize, which is why something with a low boiling point has a high vapor pressure. And something with really strong intermolecular interactions, it's harder to break or harder to vaporize, which means something with a really high boiling point is going to have a really low vapor pressure. Today we are going to be focusing on 5 different types of solids: covalent network solids, ionic solids, metallic solids, polymers, and molecular solids. And these are generalized in order of strength, where our strength is going to increase as we go up this list here. However, just keep in mind there are going to be exceptions to this. Some of our metals have really low melting points, while some of our polymers, for example, have higher melting points. So you might have some overlap between these types of solids, but generally speaking, it's going to increase in strength as we go up this list. Covalent network solids are structures where atoms are held together by strong covalent bonds in a continuous network. So because every atom is bonded in this giant framework, these solids are extremely hard, they're brittle, and they have the highest melting points of all the types of solids. So most of them do not conduct electricity since their electrons are localized in covalent bonds, but graphite is an important exception. So because its delocalized electrons are around those carbon atoms, it allows it to conduct electricity. So overall, these solids are insoluble in water because they are nonpolar and they are too strong to be pulled apart. And some common examples that you should know for the AP chemistry exam are diamond and graphite, which are both allotropes of carbon, quartz, silicon carbide, and germanium. Ionic solids are made up of oppositely charged ions that are held together by strong electrostatic attraction, which we know as ionic bonding. The strength of these interactions are going to be explained by Coulomb's law. And remember, with Coulomb's law, it's going to tell us that if it has a higher charge or a smaller radius, it's going to have stronger attractions between those ions. And because of this, ionic solids are going to be hard, brittle, and they also have high melting points because it takes a lot of energy to separate those ions. Remember, with ionic solids, in solid form, they are not going to conduct electricity because the ions are localized. However, if you dissolve it in water or melt it down, it will conduct electricity because those ions are dissociated from each other. So speaking of dissolving ionic solids into water, I wanted to quickly tell you the solubility rules for AP chemistry. They're very simple. If they have one of these ions in the compound, it is soluble in water. So when you are looking at different compounds and whether they can dissolve into water, all you need to look for is these 5 ions. And if it has those, then you can assume it dissolves in water. And since it's the only rule for AP chemistry, if it does not have one of those, you can assume that it is insoluble or does not dissolve in water. Metallic solids are made up of metal cations that are held together by metallic bonds. And in this structure, those positive metal ions are going to be surrounded by a sea of delocalized electrons. And with metallic solids, they can vary in melting points, and that's going to depend on how many valence electrons they have. So for example, if we're looking at calcium, calcium has a positive 2 charge when it becomes a cation. So for every 1 calcium, it's going to release 2 electrons. But if we're comparing that to something like aluminum, aluminum has a positive 3 charge. So for every 1 aluminum cation, you're going to have 3 delocalized electrons. So as you increase that charge, you're going to increase the attraction between the positive cations and all of the electrons surrounding it. Other characteristics to look out for metallic solids would be that it is shiny, it is pretty strong, and it is malleable and ductile. It also can conduct electricity as a solid because it has delocalized electrons that can carry that current. And remember from last unit, adding another element or metal to a metallic solid can form an alloy that has new properties. And remember last unit we talked about substitutional and interstitial alloys. Polymers are very large chain-like molecules that have a high molecular weight, and they are made by linking small repeating units called monomers through covalent bonds. So because these chains are so long, they often coil and fold, which will increase the number of sites where intermolecular forces can act. And this is why polymers are usually solids, because the combined LDFs across such a large molecule are very strong. Some polymers also contain permanent dipoles, which create even stronger interactions between the chains. And their properties, such as melting point and flexibility, are going to range depending on the length of the chains and the types of intermolecular forces that are present. Some examples include polyethylene and polyvinyl chloride, which are widely used in plastics. Molecular solids are made of molecules or atoms held together by weak intermolecular forces rather than covalent bonds. And because these forces are weaker, molecular solids tend to be soft and flexible with relatively low melting points compared to metals, ionic, and covalent network solids. They do not conduct electricity since their electrons are localized in bonds and not free to move. The polar molecular solids like sugar are usually soluble in water, while nonpolar ones are not soluble in water. And a familiar example of a molecular solid is going to be ice, where water molecules are held together by hydrogen bonding. Which of the following statements is the most appropriate based on the physical properties of solids? So A says ionic solids tend to have higher melting points than molecular solids. That is a true statement, so we're going to go ahead and give that a check mark and move on just in case there's a better answer. B says metallic solids tend to have higher melting points than covalent network solids. That is incorrect. Metallic solids tend to have lower melting points than covalent network solids. So B is not our answer. C says ionic compounds are excellent conductors of electricity in the solid phase. That is incorrect. Remember, ionic compounds are only going to be good conductors when they're either dissolved in water or melted down. So C is not our answer. And then D says molecular solids are excellent conductors of electricity when dissolved into water. And that is going to be false because molecular solids do not conduct electricity even in solution because they have no free moving ions or delocalized electrons. So our answer here would be A. All right, and I wanted to leave you with this table that kind of summarizes all of the different solids that we talked about today. If you have any questions, please feel free to reach out. I am happy to help. I hope you have a great day. Bye.